right? Let's talk about storage. This slide illustrates modern computer architecture where CPU interconnected fast QPI bandwidth and DRAM connected to CPU using this memory bus. Most importantly, I/O devices such as PCI MVN, VME, SSD, or network card are using PCI bandwidth and connect to CPU via PCI bus. So let's talk about the basics about the typical how operating system can control and data transfer to the I/O devices. So typical I/O device we require these three operation control command where can start or reinitialize or define some behavior of I/O devices using this control interface, and also data transfer. For example, you want to transfer data from DRAM to I/O devices or transfer data in DRAM to network devices. So data transfer operation. And then after performing this control and data operation, they are usually asynchronous. You have to check the status, whether the command or data transfer requests are finished. For control transfer, there are two possible approaches. First is special I/O instructions, such as in and out, for example, in x86. So operating system issue this special command in and out to access device control. So when you are issuing this in and out command, it means that this command operation interface, device interface, in and some instruction actually kind of trigger the command in the device, and you can do some operation. These of what kind of format of command is device specific, so I don't want to talk about this lecture, but these are two instructions to issuing the command to device. The other approach is memory mapped I/O. Memory mapped I/O is more popular way to access device, where in case of DRAM, in case of memory mapped I/O, DRAM, there are some kind of memory region is resolved to access device. So you can actually copying data to this memory location. So this DRAM is actually this data status command data registers are placed in the DRAM. So writing to DRAM location, your computer motherboard translate this memory write operation to device command or device control command, device data command, and status check operation. So what kind of registers are exposed to this DRAM memory map division is also device specific, but I'm talking about general way. So this internal device interface state are mapped into DRAM, and operating system access the register and command buffer or data register. They are accessed via this memory region. Okay. The second operation is how to transfer data. So PIO is port I/O. So PIO using specific instructions like in and out or some device I/O instructions that's sending data from, if you place data in the DRAM and send the PIO command, then this command are delivered to storage devices. So PIO command usually implemented in your BIOS. So this is machine specific. But I'm talking about general way to transfer data from host DRAM to device. The other way is well-known DMA. You can put the data in the DRAM and register that area as DMA buffer, and issuing the DMA command via this memory mapped I/O or memory mapped I/O. You can write some kind of data. Some command. The command specify that I'm ready to DMA, and the device in DMA controller pull out data to storage location. Okay, that's DMA. After this PIO DMA location, PIO is in case of PIO is asynchronous. So when command is issued and command never return until data transferred. But in the case of DMA, this operation is asynchronous. What asynchronous means? CPU send the command to DMA, and DMA controller and device perform this I/O data transfer operation. After that, this command controller notified to CPU. Okay, there are two ways to notify. Polling means that the status register say, oh, I finished the data transfer. So CPU can keep polling this status register. For example, in memory mapped I/O, some kind of region is registered for is used for status register, and CPU keep polling to check whether the I/O DMA operation is finished. The other way is the well-known interrupt. So interrupts device interrupt controller sending interrupt notification to CPU, then kernel takes control and handle this IOP completion via to deal with this interrupt command. Okay, these are basics of how to deal with IO devices. All right. The other thing I want to talk about is type of IO device. We can think about two different type of IO devices. The first one is this device, where this stored information is fixed size blocks, and each one has its own address. Okay, the size of block is typically 12 byte or 4 kilobyte. Okay, you can read and write this block independently using the command like this data transfer operation. Okay, so examples include disk and type. What devices I'm talking about? Block device. Okay. The other device is deliver or accept what? Stream of characters. So not block. So block is fixed size chunk, but this is single byte of character comes into stream. What are possible? What are examples of this one? Keyboard, printer, network, or mouse. Okay, these devices are character devices. Unlike block devices, for the block is bounded some address space, but in character device there's no concept of address. Okay, so they're different. For storage, we are focusing on this block type device. To access IO device, obviously, operating system and application providing a way to access device driver, which is called IO stack. So IO stack is highlight some kind of an abstract view of IO stack, where if a thread issuing the IO request, then it goes to device independent subject. What is the device independent subject? For example, operating system, storage abstraction. Providing storage abstraction, which is file system. So we will talk about later about file system. So file system is abstraction, meaning that it hides unnecessary details of device. Your sort of software consists of basic interface and functionality without using some device specific features. Okay, so for IO device. So for example, Samsung SSD, Hynix SSD, Toshiba SSD, Micron SSD, they are different. They are providing our storage devices, but having a different vendor-specific characteristics. If the general way of abstracting, this one is this vendor-specific abstraction characteristics or interface are never exposed to user application. It's hidden under the storage abstraction. Okay. Examples are naming, how to addressing files and providing protections, and some IO semantic blocking, for performance caching, and how to allocate blocks, etc. We'll deeply discuss these features in later file system lecture. The file system issuing device driver, which set up the device register. I checked that, right? Using or programmed IO or memory mapped IO, and checked status of IO operation. And the device driver issuing the device to I/O hardware. Okay, I/O hardware obviously perform I/O operation. After that, as I said, it's the interrupt handler deliver notification to device driver. Okay, device driver then handle this device specific interrupt and deliver some general message, general signal to file system. So here, from here, this link actually abstract out all the necessary, device specific features more general. So you can actually kind of by replacing device driver, you can use different hardware. Okay, these are typical I/O stack. So let's talk about more device driver. So device driver again, device specific code to control each device. So these device characteristics are provided to vendors. So for example, Samsung provided very detailed manual that if you are memory map diode Samsung devices, this type of memory can be used for this purpose, for transporting data or checking SSD status, etc. There are many details providing to as a document. And device driver write that code. And device driver using this file system API layer. Okay, so that's it hidden this vendor specific, Samsung specific command, Hynix specific command or implemented device driver layer. And here it agnostic of this vendor specific information. So that okay, so typically this device driver is written in vendor Intel or Samsung and Hynix. They write own device driver for their own devices. Okay, these device drivers are statically linked with kernel. Okay, so meaning that or some selectively loading into the system during the boot time. Okay, the other way is dynamically loaded. So Linux kernel module providing dynamic loading features. Using these features, you can load device during the execution. Okay. So again, the purpose of device driver is variety. So variety is a challenge. There are many types of different devices, very vendor specific features to operating system. Okay, and so that it has its own protocol and own data transfer implementations. So device driver hide these details to file system. Okay, so next thing we want to talk about hard disk driver. During this lecture,